All right, class, we're going to get started. Okay, so a few things to cover today. First, I just want to talk briefly about the schedule from here on to the end of the semester. Then we're going to go into finishing up the notes on lecture 17. We're going to talk about lecture 19. And then I also want to go over quiz 5. So we have a lot of ground to cover today. Any questions or anything else we want to cover before we get started? All right. So on the schedule, so if you look at the syllabus, you'll see that there's some changes to the schedule from here to the end of the semester. I had previously announced quiz 6. Originally, it was the day before Thanksgiving. Now it's going to be that Monday before, so a week from today will be quiz 6. For the lecture next week on Wednesday, so that'll be the evening before, the day before Thanksgiving. I'm going to just have extended office hours on Zoom. So I'll be available on my Zoom office hours for anybody who wants to meet with me during that class period. And then I've also changed the material for the last couple of lectures as well. So instead of going into a few examples, we're going to focus on the fundamentals of statistics instead of trying to cram multiple topics into each lecture period, which was the original schedule. Another change here that you'll notice is the suggested reading for the last couple of lectures has changed as well. So these are chapters from different books than the textbook that was suggested, and those chapters are actually in files. So you don't have to go off and buy a textbook just to support reading for 2 different lectures. Yeah, question? Yeah, so just be Zoom office hours. Yeah, for that lecture. Yeah, that's correct. Okay, any other questions? Yes. Quiz 7 can be, yes, quiz 7 can be dropped, just like previous ones. That's correct. And quiz 7 will be following the same idea. I mean, it's a quiz, not a final exam. So it's going to be covering material that's not covered through quiz 6. So, now there's a lot of it will be building on things that we've discussed previously, right? So you can't just forget everything about probability and statistics and hypothesis testing, but the focus will be on the material that we've covered since quiz 6. Yep. No, quiz 7 is not going to be a comprehensive quiz. Said all along, quiz 7 is not going to be comprehensive. So yeah. Okay, other questions? Our review, so when we do the review period here, it will be a comprehensive review. So we're not just going to talk about material that's on quiz 7. We're going to go over all the material from the entire class. But yeah, quiz 7 will be just like any other quiz. Okay, other questions? All right. So then today, to get into the material, we're going to start with lecture 17 on, where we discuss confidence intervals on variance or standard deviation. So, and again, by way of introduction, we said that there are often cases where, so to date, we've mostly discussed how we can make estimates about the mean results, right? The average that we saw within a set of experiments, or the average that we saw within a population. But there are cases where what we care about is not the average, but the variance or the standard deviation, right? The heterogeneity within the sample. And we can use statistical methods to make similar kind of determinations. But one of the things that we have to consider now is that the underlying distribution is no longer, for example, the t-distribution or the normal distribution that we used for small or large sample size confidence intervals about a mean. But now we have this chi-squared distribution that we have to consider. And one of the things to keep in mind is that the chi-squared distribution is not symmetric. And so when we're looking at upper and lower confidence intervals, we had to use 2 different values from the chi-squared distribution. Right? With the t-distribution or the normal distribution, they're symmetric. And so we only look at the critical value of that distribution from one tail. And then we assume it's symmetric about 0, and it gives us the critical value on the other tail. In the chi-squared distribution, we can't do that because it's asymmetric. So we went through, we introduced these expressions, equations 1 and 2, which allow us to, or really equation 1 was the primary one, which allows us to put a confidence interval on the standard deviation of a random variable. This is in terms of the number of measurements, the sample standard deviation, and the critical value from the chi-square distribution. Then we introduced some code which computed those values, again noting that there's a separate chi-squared for the upper and lower limit we had to compute. But then this code otherwise implements that equation, that expression in equation, in equation 1. And we looked at that for an example where we were looking at the standard deviation of, so again, some set of data, and we wanted to put a confidence interval on that standard deviation. One thing that we noted was that this all assumes that the underlying distribution is approximately normal. And so we did the check, in this case at the end, by looking at the histogram and seeing that this histogram at least doesn't look terribly not normal. And so given the small sample size, this was about as good as we would expect to be able to do. Now we have a second example. That's where we left off last time. The second example is going to follow along really in the same vein as the first example. Actually use the code that we used for the first example as well. So we have a manufacturer of sandwiches monitoring the weight of cheese per day over 80 days. So we're going to look at a histogram and calculate 95% confidence interval on the standard deviation of the population. So we load in the data into a pandas data frame and plot the histogram. This histogram looks a little bit more normal. We have more data than we did in the previous. This looks a little bit more like a normal distribution than what we had in that previous example, where we have tails going down on either side. I mean, you might be tempted to comment that it looks like it's bimodal because there are two peaks there, but this is actually pretty common when we're dealing with normally distributed random data. Depending on exactly how you choose where the bins are, for example, or how many bins you have, you may be able to eliminate that visual feature entirely. In any case, there's not sufficient data here to conclude that the data is not at least approximately following a normal distribution. In this case, in this example, we're really just using that same equation 1, which was defined in the Python code up above, to compute 95% confidence interval for the population standard deviation. So again, it's following that same equation 1, using a different chi-squared for the lower limit and for the upper limit, the sample standard deviation and the number of measurements that we made, and we obtain this result. So that the sample standard deviation is somewhere between 8.3 and 11.3. So we end up with that same result. Any questions on 95% confidence intervals for sample standard deviation? So it's just a new expression, a new distribution, but the same essential idea that we've been doing for sample means, just a different statistical test. So similarly, we can look at, we can do hypothesis testing on our sample standard deviation, or the variance if we care, right, which would be the square of that standard deviation. In this case, the test statistic is again going to be that chi-squared, or come from that chi-squared distribution. And so we're going to look at, in this case, we're given some data on silicon wafers. So they have to be ground and polished to a certain thickness. The desired population standard deviation of the thickness is at most half a mil. So we want to use significance level of alpha of 0.05 to test the null hypothesis that the actual mean is 0.5 against the alternative that the actual mean is greater than 0.5. When the sample standard deviation, and we're given that the sample standard deviation is 0.64 mil for a sample size of 15. And this is a common application of this kind of thing, right? Where when we're talking about manufacturing, there are many cases where the variance within the population or the standard deviation within the population is one of the parameters that we have to really keep under control. And so this is the kind of test that you might perform using this using this kind of test. And note here that our sample standard deviation is greater than the tolerance, right? It's greater than the specified tolerance. But what we want to know is, with the given sample size of 15, right? So we only had 15 measurements. Is that enough for us to say that we're failing this check, right? Or do we need more data? Okay. So this is, again, a common use of this. So the way we're going to construct this test is by computing a critical value of the chi-squared statistic, and then computing the actual chi-squared statistic for what we observed and comparing it to that critical value. All right, so this is analogous to what we do in, for example, with the t-test. We showed one way of doing a t-test is compute the critical value of the t-statistic, and then compute the observed value of the t-statistic and see if our observed value is greater than or more extreme than that critical value. So we're going to do the same thing here. So we first look at the number of measurements, which is 15. Our degrees of freedom is then 15 minus 1. And so for our level of alpha, we use we can use the PPF function to look up the chi-squared, the critical value of the chi-squared distribution, noting here that it's a one-sided test, right? What we care about is whether or not the standard deviation is greater than a certain threshold. So it's a one-sided test. And so we're using just alpha, not half of alpha, like we did previously. And so we have a critical value of the chi-squared statistic as 23.7. And now we're going to see, is what we observed more extreme, in this case, greater than that critical value, right? So do we have an actual chi-squared statistic that's greater than that critical value? And so we now can use our data, right? We have our sample standard deviation, so we have our sample standard deviation, and we have the sigma naught is the test, the null hypothesis test standard deviation of 0.5, and we compute the chi-squared statistic for comparing those two. And what we end up with is a result, right? Our observed chi-squared value is about 23. And we'll notice that our observed chi-squared statistic is less than the critical chi-squared statistic. And so in this case, we were considering the right-hand side tail. This indicates that we cannot reject the null hypothesis. So we do not have sufficient data in our sample to reject the null hypothesis that our true sample actually has a standard deviation of 0.5 or less. Okay, so this would indicate, if we suspected that maybe we have too much variation within our procedure, we'd have to do more testing, right, to get to a higher confidence level on the standard deviation. Okay, yeah.
So is there data and standard deviation?
Yeah, I mean, it's similar to what we saw for our hypothesis testing with the t-distribution, where let me grab a marker that's going to hopefully draw a little bit better. So one way of doing it is by just looking at critical values of our test statistic relative to the observed value of our test statistic. And what that looks like here, so if we have something like the chi-squared distribution, asymmetric, greater than 0, what we said was that for the particular chi-squared distribution with the number of degrees of freedom, in this case 14, that we have here, we said that the critical value for having an area in this tail of 0.05 was 23.6. And then what we said was, we're going to reject the null hypothesis if the result that we actually saw is consistent with is more extreme than this, right? Is more rare than this chi-squared statistic of 23.6. And so we did the hypothesis test by then computing the observed test statistic. We found it to be 23. right? It's less extreme than the critical chi-squared value, and therefore we would conclude that that we cannot reject the null hypothesis. Okay, so we could have, and we did this. We could have done this as well using by computing the p-value for this our chi-squared statistic of 23, right, 22.94, and we would have found that we have a p-value of greater than 0.05, and so we could have used that to reject the null hypothesis as well. Does that make sense? Yeah. Okay. Other questions? Okay. All right, and that concludes our discussion of lecture 17 and our discussion of confidence intervals and hypothesis tests on variance or standard deviation. Okay, so again, it just builds on what we've been doing all along. We just have, some new expressions and a new distribution that we use, but otherwise the procedure is very similar to what we had for confidence intervals and hypothesis tests on the mean. Any final questions there? All right, then we're going to move on to lecture 19. So this is about graphical representations of a factorial design of experiments. And so in this case, we're going to be discussing how we can understand what's going on in two-level experiments with 2 or 3 factors. And we're going to do this first by way of a graphical representation of what's going on, and that'll give us an idea of how to think about the effects that we can estimate from a set of experiments. And then in lecture 20, so the next lecture, we're going to go through how we can actually use what we know about curve fitting to fit curves to those surfaces and estimate what the response actually looks like to this kind of data. And both of these topics come from a different text, as I mentioned, Miller and Florian's Probability and Statistics for Engineers. And so again, I encourage you to look in files on Canvas where I have put that chapter 13. So, and this is going to build, again, it's going to build on many of our topics, but most directly on ANOVA, right, which we had been discussing for many of the previous lectures. So in this case, we're going to again do this by way of example. So we're going to say, you've been asked to optimize some new crystallization process. We believe that temperature and pH will affect yield. And so what we're going to do now is set up we call it a 2-squared design. So this means we have 2 levels of 2 factors. So 2 levels of 2 factors, 2-squared design. And we're going to present the results as shown down below in this form, where we're showing we have factor A in this first column, factor B in the second column, and we're showing these results as factor A from the first level to the second level, alternating, and factor B is shown as the first level and then the second level in pairs. And then we're showing in this case, it's a 2-squared design, and we happen to have done 2 replicates of each of those conditions. That's not part of the 2-squared. When we say 2-squared, it's 2 factors, 2 levels. It doesn't necessarily tell us how many replicates. But in this case, these were our replicate results, and this is the resulting average yield for each set of those factors A and B. Okay. So one thing in this table is the order that we presented it here. It matters for, we'll see that the order in which we present things in this table makes it a little bit more convenient to do the analysis to try to determine what is the effect of factor A versus what is the effect of factor B. Obviously, the way that we present the data in this kind of a table doesn't really affect the results, or shouldn't affect the results. At the end of the day, we should be able to construct the same analysis no matter what order we present it in. But nonetheless, the ordering of these results is convenient for the analysis that we're going to introduce in this lecture and the way that we're going to think about this based on what's in this lecture. So we call this standard order, where we have factor A, again, alternating right down this left-hand column between its two levels, and factor B grouped into, right, here's level 1 of factor B and here's level 2 of factor B. So we can think of this in a more abstract presentation shown here, where we're going to use -1 to indicate that we're at the low level of that particular factor, and a +1 to indicate that we're at the high level of that particular factor. Remember, we're only considering 2 levels of each factor in this experiment layout. And then in that case, this is standard form for our 2-squared experiment type design. So we could apply this to any other set of experiments, right? If we had, I don't know, we were looking at crop density, like in the tomato example, we had two levels of crop density. We would then, and we consider that as factor B, then we would consider the smaller level, right, as being -1, and a higher level as being +1. So we can interpret this visually as being something like the corners on, in this case, a square, or this 2-square design. This is where this is coming from, where we have our factor A was our temperature, our factor B, in this case, was pH. And now we can think about looking at our results as being on corners of this cube. So this is our result at the bottom left corner of the cube, where both of those factors are at levels of -1, or abstract levels of -1. In this case here, we have our factor A is at its high level, at +1, and factor B is still at -1, and so on to the corners of the cube. So this shows, and now what we're doing is now we've annotated these corners with the observed means of the replicates at each of those sets of conditions. And now this lets us just get a sense of what's going on here. We're going to talk about how we can actually fit a curve to something like this and generate conclusions from that in the next lecture. But before we even get there, we can see that, for example, as we increase our temperature, it looks like there's an increase, certainly, at this low level of pH, right, as we increase temperature. And there's also an increase at that high level of pH. So that looks consistent, right, in our results. And similarly, as we increase the pH at fixed temperature, right, so if we just move up those arms, we can also see that there's an increase in our result as we increase pH, right? So already from this visual representation of our results, we can start to draw some tentative conclusions about the effects that we saw within this experiment. So we're going to go a little bit beyond that and quantify what effect size we see of temperature and pH in this experiment, and then put confidence intervals on it. So, from this graph, or from this representation, we can see that the yields appear to increase with increasing temperature at both pH values. So let's start there, right? So as we increase again temperature at fixed pH, both for the low pH and the high pH, we see an increase in our average result. And so we can think of the mean, or the primary effect that we observed for factor A. We can think of a way to compute that as looking at the observed difference between the 2 levels of factor A at fixed factor B, right? So that's what we observed down here. Plus the observed difference that we see up above right? So each of those are estimates of the effect of temperature. So what we're going to do to try to find the average effect of temperature is we're going to take the difference that we observed down here plus the difference that we observed up top, and then divide by 2, because we had 2 estimates of what that impact was. And so we'll use that as our estimate of the effect of factor A. And similarly, we can do the same thing for factor B, where we think graphically, what we're doing is looking at the difference that we observed here, plus the difference that we observed here, right? So along the left and right-hand sides of this square. And this gives us one estimate of the effect of factor B. This gave us another estimate of the effect of factor B, or pH. And so we take the average of those two to get the average effect that we observed of factor B. So that's shown down here. That's what this expression is here. And so this gives us an estimate of the average effects of those factors. We can also do a similar thing for the effects of interaction, where we're going to see it. We're looking to see if there's any interaction. An interaction would tell us that, so an interaction between factor A and factor B might show us, for example, that the result up in this corner might be higher than we would expect due to the impacts of temperature or pH alone. And so we compute that by looking at the impact along this axis, so along this diagonal axis, minus the impact along this other diagonal axis, because this impact along this other diagonal axis would act in the opposite direction. And so that's captured here in this expression. The average from 4 minus the average from 3, quantity minus quantity, the average from 2 minus the average of 1. And again, divided by 2, because we can think of each one of those corner comparisons as one estimate of the interaction between those two factors. We have 2 of them, and so we divide by 2. So we're taking that. Okay, so from that we can compute the main effect of each of one of those factors, as well as the potential effect of any interaction between the factors. And so now we're going to take that table. So we take that table and we extend it to include an extra column for the interactions. Then what we can see is that this table, which again is in standard form, it's actually also showing us the coefficients for computing the effects of each parameter. And this is why we have standard form. Okay, this is why we do it in standard form, so that we can keep track of what these coefficients are a little bit more easily. This new interaction column contains the coefficients that we would use to compute the interaction term between those two different parameters. So this standard form really just simplifies writing out the effect coefficients. We have our experiment in this kind of a standard form, then, for example, for a 2-squared experiment, it should always follow this kind of a, you could use the same table for any 2-squared experiment if it's presented in the right order to follow standard form. So then this calculation is done in Python here below, and we're presenting this into an array. We're putting all this data now into an array, and then we'll compute the mean effects of each one of those factors, and the combination between those two factors in this code below. So here we see it's graphically, where we have those interaction coefficients, or those effect coefficients shown here on the left-hand side, just as we had previously, our results from trials 1 and 2, and the mean and variance from that. And from that, then, using the expressions that we wrote out above, we can estimate the effect of A, the effect of B, and the effect of the interaction. So from this, we can see that it looks like factor A has a larger effect than factor B. Interaction overall has a smaller effect, a slightly negative effect, but the magnitude of it is quite a bit smaller. But now one question we might have is this significant? Right, so is it significant that we see some effect, right? Or are those numbers significant relative to our uncertainty? And so when we're looking at the effect size, right? So what we've computed is the effect size. We can do confidence intervals on those as well. In this case, we're going to say that our confidence interval for that estimated effect has a margin of error given by this expression here, right? So it's plus or minus square root of s squared over r times a t statistic, right? So it's like a standard error times a t statistic. Same as we've been doing for other kinds of confidence intervals. The question is now, what do we use for the standard error? What do we use for the t statistic? So first of all, for that standard error, we're going to be using the pooled variance, where our estimate of that pooled variance, or s squared, is a quarter, is basically the average of the variances that we observed at all four corners of that square. All right, so for each set of experimental replicates, we had one estimate of the variance, and here we're essentially positing that the variance is the same across all corners of the square, and so we're going to basically just average all of those together. Yep. Yeah, that's saying, so increasing an increase of, let's go up to our square. So what we're saying is that an increase in temperature of, what were our values for temperature? Sorry, of 50 units results in, on average, an increase in yield of 7 units. Does that make sense? And when we're saying the effect for factor B was 3, in this case, we're saying that an increase in pH of 1 unit, on average, increased the yield by 3 units. Okay. All right, so that's our S. Our R in this case is the number of replicates, which was just 2. We had 2 replicates per condition. And then our T statistic is here going to be based on alpha over 2, right? So our level of significance divided by 2, because we're doing a 2-sided t-test, with degrees of freedom here as 4 times r minus 1. 4 because we had 4 different conditions, and times r minus 1, so the number of replicates minus 1. So one thing to note here that is a potential point of confusion. We'll look at the calculation of this in Python code, execution of Python code, but if you go back to your notes on lecture 18, and you may be looking at those notes now as you're working on the current homework, this is different from the confidence intervals on the mean difference between 2 levels of a given factor, which was discussed in lecture 18. So here this is how we compute a confidence interval on the effect size, not on the difference between 2 means of a given factor. Little subtle difference, but just keep that in mind. So this code here now computes, this block of code computes that result, it's given just up above. In this case, we had 4 degrees of freedom, and we can see all the other values that are computed here. And one thing that we see here is that the only effect size for which the confidence interval does not include 0 is that temperature effect. And so therefore we can conclude with our significance level of 0.05, because we did 95% confidence interval, that the yield increases with increasing temperature. Okay, but we can't conclude that there's any significant interaction effect, nor that there is any significant pH effect. Okay. So the next example is a 2-cube design, or 2 to the 3rd design. And so this is 2 levels of 3 factors, 2 to the 3, right? 2 levels of 3 factors. And again, in this case, we're doing 2 replications of each one of those combinations, but that replications is not part of that 2 to the 3rd nomenclature. Okay, we could do the same kind of analysis for 3 replications. We're going to read that data in, again, into a pandas, in this case, into a pandas data frame. And now when we look at this table in standard form, so this is presented in standard form, we can see each of our three factors. We have x1, x2, and x3 presented in this way. Where again, now remember there's two levels of each of three factors. So we're coding each as -1, it's a lower value, right? The lower factor for that, the lower level for that factor, or +1 is the larger level for that factor. So it's all pluses and -1s. And we have the same kind of coding for the interactions. In this case, the pairwise interactions, and then the three-way interaction are given here in the standard form. And we could use this, again, for any 2 to the third set of experiments, as long as we put it in the right order. We can use the same kind of table to estimate the effects of the factor, the interactions between the pairwise interactions between the factors, or the three-way interaction between all three of the factors. Graphically, this is the same basic idea as what we saw for the 2 squared kind of design, except now we have 3 different factors. So now instead of being in a 2-dimensional space, we're now in 3-dimensional space. So now we can think of our experimental conditions as sitting on the corners of a cube, where each dimension is one of the factors, right? So factor A, B, and C are shown here. And so those coefficients in the table that's presented in standard form, again, we can think of it as, for example, showing us like what happens, or a way to estimate what happens as we increase, for example, this axis would be factor B, right, the second factor. It would be like looking at the pairwise differences between all the corners of the cube as we increase that factor B. And we can similarly extend this to look at factors A and C and any interactions among those factors. But it comes from the same kind of place. Right, so each mean is attached to a corner of the cube. And so from this presentation, we can see that the highest means, in this case, we're looking at opacity as our readout, the highest means occur in the upper and lower right front corner, right? So here we see 7 and 7.1, and result from simultaneous increases in both factors A and B. So both factors 1 and 3 increased as we moved towards this side, and appear to result in that effect. So from this graphical representation, we can get a sense of what the responses look like over this parameter space. Right, so we would think of this 3-dimensional cube as defining the parameter space, defining the space over which we're examining these different factors. And this is giving us a sense of what the response looks like over that space, over this 3-dimensional space. But now if we want to start estimating quantitatively what are the effects, we can use the coefficients from that standard form, from the presentation of this data in standard form. And it's the same kind of equations that we used up above. But now we have, go back up here, for each effect that we're looking at, we now have 4 estimates of it instead of just 2. So now we're going to basically add up, for example, all of the raises that we saw as we increased here factor 2, right? As we move from left to right side of this cube, we have 4 estimates of the impact of factor 2. And so we're going to take each of those, we're going to add them all up and then divide by 4 because we have 4 estimates. That'll give us the average effect size. And so you'll see that we'll have a factor of 0.25 or 1/4 in front of our expressions down below. And so that's shown down here, where now this is the effect A is giving us this 0.25 of the data that we had stored, right? The coefficients that we had stored in that first column, right? Showing us which allows us to compute the effects of factor 1 times the values that we had in the mean. We have the same thing for factor B. So it's 0.25 times the values in this case that were in that second column, showing us the coefficients that we use to estimate the effect of factor B, again times the mean. And then same thing for C, AB, AC, BC, and ABC. So just to go back up here, what we're doing, so we have this column here is the mean of the replicates at each corner of that cube. We said that by putting our results into this kind of a tabular format, this is showing us the coefficients on these means that we use to estimate the effects of, in this case, factor 1, factor 2, factor 3, pairwise 1 and 2, pairwise 1 and 3, and so on. And so what we're doing, what our actual calculation here is we're just taking -1 times 4.3 plus 1 times 3.6 -1 times 3.7 plus 1 times 7. And we're doing that, we're summing that all the way down this column and this column. Divide that by 4, and we get the mean effect of that first factor. Go up here just to hit that again. When we look at the two-factor design, let's look at it here. I'm going to zoom out so we can get everything on here at once. We had our expression for the main effect of factor A. And remember, this was thinking like if we looked at, we had two estimates. Here we said in this two-square design, we had two estimates of the effect of factor A. The first was by looking at the comparison between the results at either corner of the square on the bottom, and the other was by looking at a comparison between either corner of the square on the top. And so we said that we can compute that, right, just thinking about it graphically, we can compute that as the difference that we observed down here plus the difference that we observed up here divided by 2, because we had two estimates of that factor. That's encoded into this table, right? So that same expression is encoded into this table here. We're saying that if we take minus the yield 1, right? So that's up here, minus yield 1, plus, that's a plus 1, yield 2, that's right up here, plus yield 4, right? Yield 4 has this plus 1 coefficient, minus yield 3, so there's a negative coefficient here, minus yield 3, and then divide that by 2, that gives us the estimate of that factor A. So that's how these coefficients here encode the way that we do the calculation for the effect. Okay. So the same thing, it's a little bit more complex because now we're thinking in three-dimensional space instead of two-dimensional space. But this table here computes the same thing for our 2 to the 3 design. I'll say this is maybe another reason why we use standard form is you don't want to have to think through this every time, right? So if you lay your data out in this order, in the same order, then you can just have this table, you look it up once, right? Put it into your code once and use it. And so it makes it a lot easier when we're dealing with all of that. I mean, if you're trying to keep track of that every single time, I mean, you could derive it graphically by looking at all the corners of the cubes and thinking through it, but you shouldn't have to, right? You'd be too error prone. And so by putting it in standard form, you avoid that headache. Okay, so it makes it a lot easier to keep track of. Yeah.
So when we divide by 4,
Yep. So let's look up here. So in the two-square design, we said that we have like this set of experiments here gives us an estimate of the effect of temperature on yield, right? Because we observed when we held pH constant at the low value, we saw an increase of 8 yield units, right? But because we had this two-square design, we also have an estimate of the effect of temperature on yield from this pair of experiments up above. Okay, so both of these, both the bottom and the top here, both of those pairs of experiments give us an estimate of the effect of temperature on yield. So when we want to find the average effect of temperature on yield, we're going to take those two estimates and divide by the number of estimates, which is 2. right? We take the sum of those two estimates of the effect, divide by the number of estimates of effect. In this case, that's 2. That makes sense?
Yeah.
And so down here, if we extend that to a 2 to the third design, let's consider the same effect. I'm going along this axis here. It's for parameter 2, if you notice the way the axis is defined here. So our parameter 2 is on this axis. We can see that we have 4 pairs, right? Four edges that give us an estimate of the effect of that, in this case, that second parameter on what our output was. And so we're going to add up all 4 of those effects and then divide by the number of estimates that we have, which is 4 in this case. And so that's where that 4 comes from. Does that make sense? Yeah, good question. Okay, but this is just a generalization of what we had for the 2 squared to 2 cubed, maybe more rationale for using the standard form. Okay. Other questions on that, on calculating effect size? So, yes. Yeah, we could scale this up to higher dimensions if we wanted to. Yeah, we're only covering up to 2 cubed, but we could scale this up to higher dimensions. What's that? Sorry. So you wouldn't be able to graph it, but you can still make the same kind of table. You can still make the same kind of table. Yeah, exactly. Yeah. Yeah, good question. But this would scale to 2 to the 4th or other dimensions. And we're kind of dipping our toes into an area called design of experiments, where we consider different levels of factors in order to rationally design a set of experiments exploring the impact of those factors. And these are some of the most basic kind of experiment designs, but there's a lot more in this area. Some of which you'll be introduced to in senior project, I believe. There'll be a lecture on experiment design. You'll hear a little bit more about this, but it's a whole area of research and learning unto itself. All right, so that's how we can measure effect sizes, and when we apply that to the results that we had above, we get this list of effect sizes of parameters A, B, C. Again, all the pairwise comparisons and the 3-way comparison or combination of the 3 factors. And so, but now the question is, are these effects significant? Right? Are these observed effects significant? And again, we can use the same expression here. We have this estimated effect, square root of s squared over 2r times, for a 2 to the 3rd design, square root of s squared over 2r times that t alpha over 2. Where in this case, the number of degrees of freedom is given by 8 times r minus 1, where r is the number of replicates. The pooled variance is again just 1/8, or just the average variance of all the different replicates. Again, potential point of confusion here is that it's the variance, it's the average of the variances, right? The pooled variance is the average of the variances, not the average of the standard deviations. It's the average of the variances. And our t statistic is based on 8 times r minus 1 degrees of freedom. If we had 8 replicates, each at a certain number, 8 conditions, each at a specified number of replicates. Right? Think of the corners of the cube. And so this block of code computes those results and then presents our results for effect size plus or minus margin of error. Notice that we have the same margin of error. We're using the pooled variance here. We're using the same t statistics with the same margin of error for each one of those effects, right? This is distinct from the pairwise comparison between different levels of a factor, which again was from lecture 18 that you're considering right now in your homework. In this case, we have the same margin of error for all of those effect sizes. And so when we present those results down here in text form, zoom in again, we see all of the effect sizes now plus or minus that margin of error. The margin of error is 0.56. And we can see that, for example, the ABC interaction, that confidence interval includes 0, so we can neglect it. the rate X additive interaction. So the rate by additive interaction, the AB interaction, is potentially strong, right? It looks like the strongest interaction, and that interval does not include 0. So it looks like that is significant. This indicates that the rate and additive factors cannot be interpreted individually, meaning that if we're looking at experiment results, and we cannot independently consider the effect of rate, our factor A, and additive, our factor B, on what our output is. We're going to explore this a little bit more just down below. And one note here is that whenever we see an interaction that is significant, we can't conclude that either of the two individual effects is significant. If there's an interaction, then we have to consider the two factors together. So, and then if we look at the other one here is that C, the dye setting C, this effect does indicate significance, but it's not involved in any significant interactions. There's no, like this interval includes 0, and the ABC interaction also includes 0. Additive times dye by dye, that interval also includes 0. And so therefore, we would consider, this justifies the conclusion that the higher dye setting increases the mean opacity. Note, however, that because there is a significant interaction, we found that there's a significant interaction between rate and additive. Because of that interaction, we're not drawing any separate conclusions about the effects of rate or additive. So even though these intervals don't include 0, we're not really saying anything about these things independently, because what we found is that there's a significant interaction. And so we have to consider the two. What this tells us is that we have to consider the effects of the two together, not separately. Okay, because we found there was an interaction. We're going to look at what that means in the results. So because factors A and B interact, we must consider rate and additive jointly, right? So we have to look at them together. So in this case, we're going to make what's called an interaction table, which will show this, or allow us to show this a little bit more directly. And for this table is basically like taking the results from our cube, right? So we had this cubical representation of all of our results. We're kind of going to collapse it down along that third dimension, and now we're looking at a two-dimensional representation of that data, where we've now averaged out the effect of the different dye, right? Averaged out the effects, in this case, of factor C, and we're just looking at the effects of rate and additive. And so that's what's computed in this block of code, where we're looking at the mean of, so the upper right-hand corner is the mean for all cases where factor 1 had its largest value and factor 2 had its largest value. So that's rate and additive both being high. So that's up here, 7.05. The upper left corner is factor 1 having its low value and factor 2 having its high value, and so on, right? So that gave us all 4 corners. So we took the average of all cases where additive and rate were high, for example, to get that upper right corner. The same thing for all the other corners. And now we can see that from this, it makes it pretty clear that neither rate alone nor additive alone were sufficient to increase our output, but it had to be the combination of both rate and additive that resulted in our increased output. All right, so this is why we wouldn't be justified when we detected a significant interaction, right? We weren't justified in making a conclusion on either one of the factors on their own. That makes sense? A little bit more sense. So because when we saw our most significant result when we combine the two together, right? You have to consider the effects of the two, of rate and additive together in order to really understand what's going on. So the effect of the dye to increase opacity, the effect size was about 0.8. And the dye did not appear to interact with any of the other factors. rate and additive both interacted and therefore could not be interpreted separately. And we estimated the effect size as about 1.7 overall between the two. So again, the higher additive amount, higher rate, and increased dye setting were all desirable if we wanted to increase opacity, which was our output in this result, in this example. All right, any questions on this? That's the end of our lecture 19. All right. Well, then I'm going to give, or we'll take a break here. We'll give everybody who wants to clear the room to get out if they'd like to, and then we'll talk about quiz 5. We'll go over the questions on quiz 5. All right. Thank you all.